So now in this video, we have a 555 timer wired in monostable mode. I don't have a specific voltage there, but again, it's monostable mode. I press the button, the output goes high for a set period of time. That's not the stable part. What's stable is that the output's gonna be low. It's gonna stay low until I set the output high. So there's one stable state that is low. You know, when it's high, it's only going to be high for a period of time before it goes low right there. So this is stable until I force it high. You know, low is stable until I force it high. And again, it's you know, basic 555 monostable mode. But usually I show, and most people probably show it being powered with 5 volts. But here we're going to deal with higher voltages. So it's really common now to have 12 volt lithium iron phosphate batteries. It's not 12 volts though that you're working with. That's kind of the lowest voltage that the battery will get when you discharge it. You can't get it to 10 volts, but it's good to stop discharging at 12 volts. When you apply a charger, you know, if you got a circuit, you know, maybe that circuit's going to be working while the charger is applied to the battery. You know, you could have 14.6 volts being applied to that battery, and thus the circuit. Now when you remove the charger, or you know, the charger turns off or goes into a float mode, the charger might try to hold the battery at a 13.6. The battery will hold itself at 13.6 if it's charged. But any case, you know, when you remove it, you got a lower voltage. So this is really only like a temporary 14.6. But again, you got to have circuitry if you attach it to the battery that's ready for that. So first off, instead of 10K, I used 100K right here for the pull-up resistor to pin number 2. So you know, it doesn't really matter the value that you got, but we're going to waste less current with this pull-up resistor. That keeps a, you know, keeps whatever voltage we got to, it's 14.6 right now, to pin number 2 right there, but it's 100,000 ohms. So if I press the button, and by the way, if I keep holding the button down, the output's not going to go low as long as I hold the button down. But any case, we had 5 volts. Now I'm making a direct connection to ground right there. It's direct, so we got 0 volts, and I think it's been long enough now. If you hold it, output's going to stay high, but as long as you exceed the timing, then the output will go low when you release it. So be aware of that when you're dealing with monostable mode. And so yeah, I bumped up the pull-up resistor here, but 100K might, you know, even work at 5 volts. So, you know, but people generally have a lot of 10K resistors, I think, is why you usually see it for like a pull-up resistor. So yeah, that keeps, right now, voltage is high. Pin 2 is waiting for a low input. It's just waiting for a voltage, less than 1/3 supply voltage. We close the switch, we get that, and a low voltage to pin 2 sets the output high. Now, we got the timing part of this. And again, 470K, 10 microfarad capacitor right there sets the timing. When we set the output high, the capacitor starts charging. When it gets to 2/3 supply voltage, pin 6 will sense that. Then it instantly discharges and the output connects to ground. You know, again, basic monostable 555 timer stuff. Now, one reason why I made this circuit is I make a lot of demonstration circuits with 5 volts. And there's, you know, higher voltages out there that you might want to build circuits with. But I think the majority of them are 5 volts. You can take a buck converter, you know, I have something that you clamp to the battery and it outputs USB, which is 5 volts. You know, you could get buck converters that take a higher voltage and actually convert that power into 5 volts. But also you can just attach this directly to a 12 plus volt circuit, 12 to 15, just by changing the value of the component. So usually I use a 1K resistor for 5 volts to protect the blue LED. Simply, we don't need much current for the blue LED, so we simply bumped up the resistance there. Basically, we doubled it. We're going to get a little less current, but then 5 volts with the 1K resistor. Actually, no, we're going to get a, somewhat close to the same, 2.2K. And because we raised the voltage by, probably about 2.2 times as much. So yeah, we should get about the same there. And for the high though, now we got the high output. You see we got two resistors. So I kind of want 1,000 ohms to protect the red LED there from 14.6 volts. And that's what we got at the power supply right now. And I'll also show, I use the bottom of the board as storage. Those components, they're not attached to the rail or anything. They're all disattached. But yeah, we might be able to go down to, or we'll be able to go down to 12 volts. And that'll still be enough voltage to power this circuitry. Our components here are just intended to be able to handle up to about 14.6. So there you can see we went to 12. That doesn't really matter. We just want to make sure it works in the full voltage range. So I got two resistors right here. So you can see we got the red LED, long lead anode up there, short lead cathode down there. That's because a 1,000 ohm resistor, the LED drops about 2 volts, and the output actually doesn't output the full positive supply voltage, but let's assume that it does, just to be safe. With 14.6 volts, the red LED will drop a couple volts. That could put 12.6 volts across the resistive part of this protection circuitry. So a lot of times it could just be one resistor right there, but they're rated for a 1/4 watt. Last couple of videos we did the math. Maybe I'll pop it up on the screen. But in any case, they're 1/4 watt, 0.25 watts. You still want to keep the 1/4 watt resistor. All of these resistors are 1/4 watt right there. You want to keep them below, well, their maximum is 0.25 watts. That's 1/4 watt, but you want to stay below half that, 0.125. And because they get really, really hot at their maximum wattage. You want to stay like halfway below that, and or less, and that should ensure that they last a long time without burning out or being otherwise damaged. So yeah, one resistor there, 12.6 volts. That's a lot of voltage for how much current it will pass if it's a 1,000 ohm resistor. So we take two of them, about half value right there. 470 is more common than 510. And I don't know how common 500 is, but I don't think I have any. So I put 470 there. It's close enough. We'll get a little bit more current, but that's fine. We're still within safe limits. But there's two of them. So the LED drops a couple volts. Again, we're not going to get the full voltage out. We're probably going to lose at least a volt coming out. But let's just say we get the full voltage. So 14.6 subtract 2. We got about 12.6 volts across the two resistors in this case. If it was just one resistor, it would also have 12.6. But since there's two of them in series, they will divide that voltage in half right there. And the wattage that a particular resistor is the voltage across it times the current going through it. So if you got two in series that are half the value of a lone resistor, then their two resistances will add up to about the same resistance, but there's two of them. They'll divide the voltage in half. So ultimately, each one of these resistors will get half as hot as if there was a lone one. So hopefully that makes sense. But that's kind of my solution when you got some more voltage than what the components can handle. In this case, it's due to wattage, how hot they're going to get. You can simply put them in series if they're resistive components, and they will divide up the voltage. We could also just take more LEDs and put them in series, and that would lower. They all drop the voltage that goes across the resistor. I've done other videos with that, but it gets challenging. You learn probably a lot of circuits at 5 volts. Now you got to work with 12 volts or maybe even more, and you can't just assume that you can double the value of the components because you got twice the voltage. When it comes to wattage, it's voltage times current, so the voltage will go up, the current will go up, and so you got a lot more wattage than twice as much. You probably got like 4 times or something. So, any case, yeah, that's it. Hope that all made sense. Thanks for watching. Make sure you check out one of the videos posted to the screen, and check out links down below. They all help out a lot. I'll see you in the next video.